As you can see from the slide in front of you, our speaker today is Ben Zuckerberg from the Department of Forest and Wildlife Ecology. His talk is the second of the week after Doug Maxwell's on Monday. It's a pleasure to have you here.
Excellent. Yeah, thank you very much. And hey, good on you all for being here on such a gorgeous day. So you are one committed group. So today I'm going to follow up on Stan's talk on Tuesday where he talked about phenology and climate change, and really with a focus on birds and some of the recent work we're doing and have been doing over the last several years. And the way I always like to start these talks off, this is not a model. These are temperature records going back to late 1800s. And what you're going to start seeing here is one, there's a lot of variability in temperature across the globe. But starting around the 1960s, 1970s, you're going to start seeing a pretty amazing change in the climate of the world. And during that time then, what we've seen over roughly about a 100-year period is a pretty amazing warming pattern, such that we've seen about an overall 1 degree sort of Celsius increase in global average temperatures. And many of these areas that we know to be warming the fastest tend to be sort of these more northerly latitudes over here and over here. And all those hatch marks that you see are significant trends at a grid scale. So what you can see right off the bat is that there are a lot of significant trends, and there are very few areas that are blue that are cooling, that are significantly cooling over that same time period. What I would say, though, is that we know that this warming is very heterogeneous over space and over time. So if you actually look at it within the United States, there are definitely areas that are getting warmer faster, parts of the Northeast and the upper Midwest and the Southwest, and that there are what we refer to as warming holes, especially in the southeastern part of the United States, that are cooling in some areas, but what we know now is that that warming hole is beginning to close. And we've also seen changes in precipitation too, with some areas getting wetter, especially in the Northeast and the upper Midwest areas, and some areas getting pretty significantly drier over the last 30 to 40 years. And one thing I always like to point out too is that we talk about clearly is attribution and what is sort of causing these effects, and certainly CO2 and carbon dioxide in the atmosphere is definitely something we always consider to be a driver of this. And I always like to put this a little bit in perspective. So they've done reconstructions of CO2 in the atmosphere going back 20 million years or so. And this is kind of what those reconstructions show on average. This is where we are, that black line there. That's about 400 parts per million in terms of CO2 in the atmosphere. And this is where it's been for the last 800,000 years or so. So you can see we really are in sort of a novel space when it comes to CO2. And these are the projections. So this is 2.6 or so RCP, which is basically sort of the best case scenario. We stop fossil fuel emissions like tomorrow. We're still going to be at about 400 parts per million, going outward to about 100 years. But this is the track that we are on right now. We're going to be roughly about over 800 parts per million of CO2 in the atmosphere. This is an interesting little exercise that they call the pulse. And what this basically represents is that if we actually, right now, today, burned off all the fossil fuel that we've already brought up out of the ground, that's in people's gas tanks and so forth and so on, and we just burned all that all in one day, that's the level of CO2 that we would have in the atmosphere. Okay? So that's already out of the ground. We're already going to account for it in one way or another, and we're going to be well over 2,000 parts per million. You're looking back 20 million years or so, and we really are in sort of a novel area. And that's how long it takes in order to even get down to this level here of about 1,200 parts per million over 1,000 years. Okay? So we really are sort of encountering sort of this new sort of area of climate and what we expect to see in terms of climate change, particularly when we start looking at projections of temperature and precipitation. This is what we've seen in the late 20th century, this is middle 21st century, and this is late 21st century. And you can start seeing here, these are the general increases. And remember what I said, that what we've seen in terms of modern climate change has been about 1 degree. What we're projecting out is anywhere from 4 to 6, even 12 degrees warmer over the next, by the end of this century. In terms of precipitation patterns, what we're expected to see is that drier areas are going to get drier, wetter areas are going to get wetter, and so those differences between sort of dry and wet areas are expected to increase over time. So all this then, sort of what we now recognize is that the warming of the climate system, especially over the last 30 to 40 years, is unprecedented, especially over the last 1,500 years or so. The last 30-year period has been one of the warmest over the last 1,500 years. We've seen rising temperature, altered precipitation patterns, milder winters, earlier springs, rising ocean levels, and a higher likelihood of extreme events. So then this leads to this question then, especially with birds and wildlife in general, is what do? Okay, and they have three main options here. They can go extinct, they can move, or they can adapt. Okay? And what I would say when I do talk about this, and certainly when scientists talk about this in general, that we oftentimes do focus a lot on this idea that there have been pretty amazing changes in the Earth's climate system in the past, right? We've had glaciation, we've had interglacial periods. So we've had big periods of pretty amazing changes in the Earth's climate system. So why can't, and many of those species that actually went through those changes still exist today. So why can't they just not adapt? Why can't they just sort of be able to do what they've done in the past and persist? And so I would say that there's a couple of reasons why we would actually expect this sort of process of adaptation not to play a part or be as effective as it's been in the past. One of them is that the rate of warming, as I kind of mentioned over the last 30 or 40 years, is unprecedented. Okay, when you look at 1,500 years ago, when you look at different periods of time, there have been periods of warming up, but the rate at which we are on that trajectory, we are quickly going outside the bounds of any of that sort of historic variability. The other is that we have pretty significantly altered the Earth's template, right? Well, now that over 40% of the Earth's surface is tied up in agriculture, many of the same pathways and escape routes that species have used in the past to accommodate climate change no longer exist for them. So those are two main components that I would say that I sometimes talk about when we try to sort of buffer this response out, well, that species can simply adapt to environmental variability. Well, it may not be that simple. So what I'm going to talk about today then are some of the lines of evidence that species are in fact responding to climate change. I'm going to kind of broadly touch on all these topics in very sort of quick ways. One of them is this idea of range shifts. The other is community shifts. The other is migration patterns, population declines, and disease. I'm going to give you sort of evidence that we've sort of collected and others have collected over time that started to sort of try to disentangle and quantify these responses. So first, range shifts. So back in the 1990s or so, when we really started thinking about the ecological responses to climate change, one of the sort of the broader and sort of, I'd say, well-known predictions was this idea that species will in fact shift their distributions, shift where they are occurring in response to climate change. And the main prediction was that if we have in fact warming, let's say throughout the northern hemisphere, what we expect to see is that southerly and sort of warm adapted species would shift northward, especially along their sort of range boundaries, their distributional limits, and that cold and winter adapted species would actually shift northward as well. And we refer to these as these poleward shifts, okay? And so this sort of systematic shift is something that people really wanted to start quantifying and seeing if this is actually playing out over time. And one of the areas, and I know Stan kind of talked about sort of the importance of sort of long-term monitoring data, long-term natural history data, but one of the areas that people really started looking at were breeding bird atlases. So those of you who are not familiar, breeding bird atlases started back in the 1960s. What these are, you can imagine this is New York State, but we definitely have one in Wisconsin too, is that people go out and they can visit these 5 by 5 kilometer blocks. And within these blocks, they record what birds that they're seeing. They record their sort of level of breeding activity. And they do this, these are all citizen scientists, these are all volunteers, but the amount of data is actually pretty good. So there are over 400 atlases that are conducted really throughout the world, from very local, almost sort of county level sort of atlases, all the way up to continental wide atlases. And now about 70% of them are actually repeat atlases. And the real advantage to repeat atlases is that you go out there and you can detect change. So here we've got a southerly, warm adapted species. Anybody know what bird this is? Anybody? Come on, any birders? All right, like a wren. So this is a Carolina wren, right? And by its namesake, you would expect this is to be a sort of warm adapted, southerly adapted species. So if that prediction held true then, what would you expect to see is happening in New York State? Would they be increasing or decreasing in terms of their distribution?
Increasing.
What?
Increasing.
All right, excellent. And that's exactly what's happened. So in 20 years, okay, their population, their distribution increased by almost 300%. Okay? So you've got this really nice, powerful data set in which you can actually start being able to look at distributional range boundary shifts for these species. And because they're repeated throughout the world, what we've actually been able to see is this poleward shift, and that repeated for across many different species in many different areas of the world, that this poleward shift is in fact happening along these range boundaries. What about the future? Well, a lot of groups like Audubon are actually actively trying to model then not just how they're shifting northward over time historically, but what do we expect in terms of the future? And so they are building these bioclimatic niche models that basically capture the climate space for individual bird species. And so that sort of dark line here is the wintering distribution for loons now. And you can start seeing, and that's their summer distribution in yellow, they are beginning to move up, or what they're projecting is that northward shift northward. And so much so that they've estimated that over 300 species will lose more than half their climate space by the late century, if these projections hold up. So this sort of first idea of range shifts, now that we've kind of been able to quantify it, it's one of the great signals that, in fact, species are responding to climate change. More than half of observed animal range boundaries have already shown a response that we would expect to see in modern climate change. Okay, so the next question is that if you're actually seeing that these individual species are moving poleward or moving northward or shifting their distributions in one form or another in response to climate change, are we actually beginning to see entire shifts in communities? Right? Because one of the things that we have been able to find is that some species are tracking climate faster than others and some are not tracking at all. And so if that was the case, you'd actually begin to start seeing sort of a reshuffling of animal communities. So we wanted to actually quantify this. We wanted to actually see whether or not this community composition is changing over time. And so one of the data sets that we looked to actually quantify this or measure this is data from Project Feeder Watch. So Feeder Watch is a citizen science program. It's one I've been working with for, I think, over 10 years now. It's been running since 1987. It's run through the Cornell Lab of Ornithology and Bird Studies Canada. And what this is basically people watching their feeders. Okay, they watch their feeders. They record what kind of birds are showing up on their feeders. They record the maximum number of them that they see at any given time. Okay, and they actually upload this online. They can sort of show exactly where their feeder is using Google Maps. And this is a really nice, robust data set. Over about 20,000 people participate every year, and they contribute almost, about 6.8 million bird observations per year. So this is a big, robust data set. Each one of those points, those blue points, represent the Feeder Watch site. So you can actually start seeing how we can begin to capture these community shifts in wintering birds over a fairly long period of time. So the hypothesis that we had going into this was that if wintering birds are in fact limited by climate in one form or another, then can we actually begin to see that communities themselves are being altered by climate change? So going into it, the idea here is that if you're, let's say, a Feeder Watch participant and you're outside and you're kind of watching your feeder, you might see a community of birds like this, where you might have, let's say, a cardinal, a tufted titmouse, a Carolina wren. And so as you kind of move upwards or northward in terms of your location, maybe if you're living in the mid-Atlantic states, you may have very similar species, but maybe a few of them are sort of in lower abundance or higher abundance. Maybe you start getting different kinds of species, like a junco or chickadee start showing up at your feeder. And as you kind of get up into the Great Lakes region, well, maybe you start having a very different kind of community of birds. You start having tree sparrows, you start having white-breasted nuthatches at your feeder. So we can actually capture this. And the way we kind of capture this different change in this bird community is what's referred to as the species temperature index or the species thermal index, the STI. So what this basically does is it measures the long-term temperature experienced by an individual species over its entire range. So the way you can think about doing this is that if you've got information on climate, which we have lots of now, and we've got information on the distribution or the occurrence of a species over its range, you overlay that, okay, you can capture the overall sort of climate that species persists in. And that basically gives you an STI, in this case of minus 6.77. So that number itself actually is not all that valuable. Okay, it's just telling you the average temperature that species exists at. But if you compare it to another species, then you can see that it's generally, and this is minimum temperature, a little bit warmer for this eastern Phoebe here, meaning that its distribution is a little bit more southerly distributed. Okay, so this is a really useful measure because what you're basically doing is you're assigning each species within a community this index. Okay, so the nice thing is you can take all those indices, you can basically average them across a community, and for one community of birds, let's say, you get what's referred to as a community thermal index, and that's or temperature index. And what that captures is basically the balance between cold and warm temperature dwelling species. All right? You can weight it by abundance, you can do a bunch of different things with this, but that really is sort of the metric that you're using. So if in fact then warming is happening and we're seeing sort of warm adapted and southerly adapted birds sort of being able to begin to dominate systems, what you would expect to see over time is that CTI will change, that community thermal index will change. So if, let's say, warm adapted species are becoming more common, more abundant, what would you think? CTI goes up or goes down? Come on, any brave souls out there?
Goes up.
Yes, thank you very much. So you expect it to go up because they're becoming more dominated by these warm adapted species. And that's exactly what we found. Overall, throughout the eastern United States, that over time, throughout this, with these wintering bird communities, that the community temperature index generally increased from 1990 to 2012. But we wanted to look at across latitudinal gradients. And what we really expected to see was that most of those changes would be occurring up here. But that's not what we found. We actually found most of the biggest changes in CTI were occurring in these southerly latitudes, which then sort of led us to sort of try and understand what species are driving these changes. Okay, and we kind of did this sort of fancy statistical approach where we kind of take one species, we take another species, put them back and put them back to try and see which species are really driving this pattern. And so what we basically looked at was what's referred to as species contributions. And here, these were the traits that we wanted to focus on: body mass, northern range boundary, and whether or not they were increasing their distribution. Okay? What we found was that the species that were really driving it tended to be smaller bodied species. They tended to be species that were more southerly distributed, and they tended to be species that were increasing in their distribution. Okay, they're increasing in their abundance in many of these areas. Southerly distributed species, or sorry, smaller bodied species tend to be much more sensitive to variation in temperature and much more sensitive to things like cold snaps. So the less cold snaps you have, the warmer you have in terms of these winter temperatures, these smaller bodied species can take advantage of those warmer temperatures. So in general, what we found from this study here was that this group of community of birds is beginning to take over, or beginning to sort of reshuffle this community of birds. And it's being driven by these warm adapted birds taking advantage of these warmer temperatures, smaller bodied species that were southerly and increasing in their distribution. So that was sort of one example, but what about the future communities? And that's sort of what I showed there is what we've seen over the last, let's say, 20 years or so. What do we expect to see in terms of future communities? And there's been kind of really neat work where you can kind of take these distribution models and then project them into the future, kind of like I showed there with the Audubon. And here, this is wintering bird species richness throughout North America, or throughout the United States and Canada here. And you can see that wintering bird species richness goes from about 157 species all the way down to 11. That generally, there's a little bit more species down here in the southeastern part of the United States. This is breeding bird species richness now, about 72 to 9 species. These are kind of hot spots of breeding bird species richness here and here. And then the projections then forward, what would we expect to see with wintering birds, do you think? Would they be increasing or overall or decreasing?
Decreasing.
Decreasing? I got one for decreasing. Any other predictions there? That's right. What about breeding birds? Do you think they're increasing or decreasing? What's that?
Decreasing?
Decreasing. So in general, what we see under future scenarios is that wintering birds are going to generally increase in species richness throughout most of North America. But some areas, like the Panhandle and southern Texas here, we are seeing a decline in the number of wintering birds. A lot of areas are showing a decline in breeding bird species richness, except in areas that are much more northerly sort of situated, the boreal Canada and so forth. Okay, so we're beginning to get a sense of how these communities are going to change over time. So let's talk about migration then. And I think Stan went over some of the sort of neat evidence out there about migration patterns and earlier migration patterns, and sort of noted how Leopold and others kind of were some of the first to kind of obviously put forward the importance of phenology, taking observations of when species are showing up, or when you get flowering times or calls and things like that. So we're kind of in a new age now, where a lot of these observations are being collected by sort of citizen science at broader scales. And so going back to that feeder watch data set, it can actually be really useful for capturing phenology as well. So here we've got the American robin, and this is showing from based on feeder watch data, areas where we see lots of robins, areas where we have few robins, and areas when we have no robins. So if we kind of look at the upper Midwest here, you can see, yeah, there are some robins scattered about, but for the most part, they're generally not wintering here as much as they are kind of down here in the southeastern part of the United States. So that's January. And this is February, and you can see that pattern is still kind of holding true for the most part. And then this is March. And you start seeing that migration, that early spring migration as they kind of come through the upper Midwest, and you start seeing how we start seeing more of these birds coming in and basically coming in from the southeastern United States. We can do this for roughly about, with feeder watch data, it's really cool, it's really good at getting at these sort of earlier spring migration events, and we can do this for roughly about a dozen or so species. And when we've done this, what we have shown pretty consistently is that, in fact, yes, spring arrival is happening earlier. Many of these are short distance migrants, so that they can kind of take advantage of the different sort of weather conditions, more so than like neotropical migrants that are coming from Central and South America. And what we have shown too is that we can capture not only their sort of first arrival, but also what we refer to as their median arrival, when the entire population is kind of coming. The first arrival usually captures, I'd say, those sort of the first few individual birds that are kind of coming into an area, whereas the median arrival is kind of capturing the full population. And these things don't always happen in lockstep. So what we are beginning to see is more non-uniformity, meaning that these sort of arrival patterns in terms of first arrival and median arrival are happening at somewhat different times due to sort of these earlier springs. Sort of another kind of neat study that was done was looking at nesting data. And this was a really cool work that's done by Peter Dunn, who's at UW-Milwaukee, and Dave Winkler. And what this really takes advantage of, at the Cornell Lab of Ornithology, they've had a nest record card program going back to 1966. And in fact, when I was a research associate there for a couple of years, and actually my office was right next to a whole set of drawers. And if you opened up these sort of drawers, you found these just stacks and stacks of these nest record cards. No one had ever digitized them. They're just like these troves of these nest record cards that have been sort of being collected over 20, 30, or 40 years. And so if anybody ever wants to do a PhD or something, let me know, because it's amazing. This would be a really awesome sort of data set. So Peter Dunn and David went through and they collected nest record cards for tree swallows. And this was kind of an interesting idea in the sense that tree swallows are migrant. So clearly they would be very sensitive to this. They're also nest boxing species. So it's really a lot easier for participants to go in and kind of check a nest and see when that bird is sort of nesting, laying eggs. And what they were able to show was this very distinct increase 9 days earlier over about a 30-year period of nesting. So not only are they getting here earlier, they're actually nesting earlier. And all that nesting tended to be explained by May temperature. So that early spring temperature. And that's a fairly uniform pattern that we see in a lot with a number of different species, that they're actually not only arriving earlier, but they're beginning to nest earlier. What I would say, though, is that that's not the case for all birds. And primarily, this is what we refer to as a phenotypic mismatch. Okay, and the idea here, and the concern that a lot of sort of scientists have, is that if you've got sort of birds, like a pied flycatcher here, that require some sort of food resource, let's say caterpillars, and when those caterpillars are kind of erupting and budding out on a landscape, then what you can imagine is that their arrival to an area is timed and has evolved very specifically to take advantage of that food resource, right? So here you've got sort of the food availability, it kind of peaks. The bird has kind of arrived here, and it's going to take advantage of that food resource. Now, it's not necessarily that the adult bird coming is going to really try to hit that resource peak right there. They're coming a little bit before. Why are they coming before? Why do you think they need that peak resource? Not like exactly when they arrive, but a few weeks after they arrive.
Find a mate and nest.
Yeah, so what's that food resource for? What's that resource availability for? For the chicks, right? So actually they have evolved to come to predict almost when that food resource is going to happen, not necessarily for their own survival, but for their nestlings to really take advantage of it. Okay? So what we're seeing though is that when these birds arrive, especially these neotropical migrants, is not so much guided by temperature. What do you think they're using to tell them to get to their start migrating?
Sun.
Or sun, yeah, and day lengths, right?
Yeah.
So they're very tuned in with day lengths and photo period. Okay, and that actually they'll start doing what's referred to as migratory hopping. They'll start heading in the right direction, and then they'll take off. And all that is cued by day lengths. Is day length changing? No. Temperature is. So most of the resources that they're taking advantage of are these insects, these caterpillars. And what you're seeing is that those caterpillars are much more sensitive to warming temperatures and they're erupting earlier. Okay? But that arrival time remains fixed.
You know what,
Yeah.
doesn't this just make people who do what you do wonder about why can't the future be here now so that we can develop interspecies communication so the birds get on the line with the whoever that deals with the insect population and they can coordinate their arrival?
Yeah, and some of them are better at it than others. So like short distance migrants I talked about before,
Yes.
they are actually have a bit of a competitive advantage because they are able to take advantage of this more than these migrants. And the problem is that these long distance migrants in particular are increasingly mismatched with these caterpillars. And what they've shown is that the areas where they're most mismatched, and actually these tend to be the most northerly sites, because that takes longer for these birds to get there, they're having 90% declines in their populations, in the bird populations over those two periods. So what I would say, though, is that this is awesome work that's done by Christian Both back in the 2005. This is still controversial. And primarily it's controversial because in some cases birds can actually I wouldn't say have advantages to being mismatched, but what it does is it reduces competition. So the nestlings basically are in some cases, have a little less competition for those resources. But in general, the worry is this idea of phenological mismatch and the idea that certain species are increasingly asynchronized with their food resources. Okay, so let's shift on to population declines. Okay, and so one group of species that I've always been particularly interested in are grassland birds. For those of you who don't know, these are birds that are clearly honed in on sort of open areas. They've been really hit hard primarily by habitat loss, the conversion of tall and short grass prairie to agricultural areas and suburban, exurban development, removing that kind of habitat. Here you've got bobolinks, eastern meadowlarks. You see those red areas are areas where they're showing population declines of over 1.5% per year, okay? You can see this sort of pattern here is pretty consistent among all grassland birds, okay? In fact, out of all the guilds or groups of species that we know throughout North America, grassland birds are the ones that are declining the fastest over the last 40 years or so, okay? So there's no doubt in my mind that what primarily is driving this sort of pattern is habitat loss for grassland birds. But what we've been really interested in is whether or not sort of the effects of climate change, drying conditions, and warming temperatures are going to exacerbate these losses in any way. And so what we've been able to do is actually sort of model sort of what we refer to as the demographic niche. So The idea being sort of where are their best conditions going to be for nesting success for these birds. And we've done this with Senso sparrows here. And what you can see is that those areas that are sort of red and yellow are really good nesting success. Those areas that are green have very low nesting success. And for this species, when we predict it out into the future, what we're predicting and projecting is an almost complete demographic collapse right up until here, which is sort of the core of their area. And what's really driving that is precipitation and changes in precipitation for these species. And what we're really concerned about with grassland areas is if you think about being able to be buffered, from extreme events like rainfall, like flooding events, if you're a grassland bird, you have absolutely no coverage whatsoever, not like forest breeding birds or other species. So when we actually look at it, so what we actually did was we actually looked at about a dozen different grassland birds. We took about 81 studies and looked at about 21,000 different individual nests. And what we actually were able to see was that in some cases, bio-year precipitation, which is basically the amount of precipitation a grassland receives about the year following, the year right before the breeding, actually increases nest success. So the wetter conditions they actually do a little bit better. The grassland is a little bit more productive, you have more insects, so that makes a lot of sense. But during actual breeding, when they're kind of settling in for May, June, August, it's a negative relationship. So when you have too much precipitation occurring in these areas, when you have lots of rainfall, then you basically reduce overall nesting success, okay? In terms of May temperatures, basically, you want to get away from the very cold and the very warm here. Okay, and both those conditions, those extreme events, tend to reduce nesting success, really dampen it. The interesting thing that we wanted to explore here, though, was that for many grassland bird managers who think about managing grasslands, they really like to try and think about big grasslands. Because when you have smaller grasslands, you have sort of a higher likelihood potentially of those populations blinking off. Okay, and what we found was that many of the effects of temperature on nesting success was really driven by that patch size. So much so that in those sort of smaller patches, the negative effects of May temperature were much stronger. And when you start looking at bio-year precipitation, the positive effects of that precipitation were much stronger in those smaller patches. So that patch size, or how big those grasslands are, really influence the impacts of temperature and precipitation on these sort of grassland bird populations. Okay, so the last sort of case study I want to talk about is what I like to refer to as death and pestilence. And so in this case, there's a lot of interest out there as to whether or not climate change could in fact increase disease risk for a lot of wildlife populations. And so I don't know if any of you are familiar, but every now and then, especially in the Great Lakes, we get these big sort of mortality die-offs of birds, these big sort of mass die-offs of birds. And we've been having this happen really for a fairly long period of time, going back to the 60s, where suddenly you get sort of thousands of birds showing up on the shorelines here. You do have these sort of episodic periods where they kind of go away, but then they start coming back and they start just to show these sort of big mass mortality events that happen. And we've seen this in Lake Michigan, Ontario, these big pulses. And as you can see here, it's getting increasingly a problem. And we're talking about thousands and thousands of these water birds coming up on a shore. So can anyone guess as to kind of what may be driving this? So a lot of what we're concerned, sorry, did you?
Is it temperature?
Well, but what's the mechanism? It's not necessarily they're getting too hot and just dying. Has anybody heard of anything referred to as avian botulism? Okay, so this is a really sort of interesting sort of disease and problem out there. The reason with the threat of avian botulism is really due to this sort of anaerobic bacterium that evolves. And it's this botulism type P that kind of pops up in the Great Lakes every now and then. It produces this bacteria in anaerobic conditions, meaning oxygen poor conditions. It will produce a neurotoxin. That neurotoxin gets into the food chain, and if birds contract that neurotoxin, you can have this loss of motor control, you have this eyelid paralysis, and what ends up happening, it doesn't actually kill the bird straight up. What it does is it does this referred to limber neck, meaning that they can't keep their head above water. Okay, so they basically cause a paralysis and they end up drowning. as their head goes down and they lose control of their neck. And so it causes respiratory distress and these big mortality events.
What are the conditions whereby this spore-forming bacteria occurs? Are you going to explain that to us?
Algae. So what they really do consider happens, or what there's some debate about this, but what they do feel happens is that in very clear waters, and so we have zebra mussels, right, infiltrating a lot of these areas, a lot of the lakes, it actually causes more clear water, which allows for more sunlight to penetrate, and a higher growth of algae mats, cladophora mats. And these big sort of algae mats then, with warmer temperatures, generally are the perfect breeding grounds for this type of botulism, for this bacterium to propagate. And then, if you got enough of this in the system then, and you start higher and you got lake bottom and sediment and the algae and the building up of this bacterium, it then begins to propagate through the food chain. It goes up through crustaceans, it goes up through bivalves, you can get it through bivalve eating fish, and then of course it goes all the way up through this biomagnification process to these water birds. And so we actually worked with the USGS and the National Wildlife Health Center, and they started what was referred to as the Avian Monitoring Botulism Citizen Science Program. And what this basically was a group of people who went and basically did these very fixed transects along the Lake Michigan shoreline. And they repeatedly went by and actually collected information on when carcasses started becoming deposited. And this is a really nice citizen science program that went on for about 3 to 4 years. And they were able to kind of capture not only the seasonality of these big massive die-offs, but the spatial distribution of them. Where were they happening? And so we looked at this for a number of different species when they started showing these big mortality events. And where were they occurring and when were they occurring? And we were able to couple it with information on lake temperature data and also on the presence of cladophora, those big algae mats. And we used this we were able to capture this using satellite data. And when we combined that with the information from the AMBL surveys then, we started actually being able to see that when you had warmer temperatures, the higher prevalence of these algae mats, it actually synchronized these big mortality events. So this was an important finding in the sense that these mortality events weren't happening sort of randomly in different areas, that when you had these pockets of warm water, when you had the presence of these algae mats, over 40 kilometers or more, so almost 25 miles or so, it would synchronize those big mass mortality events. And the problem is, and what we're concerned about, is that most of the future projections suggest that lakes are in fact going to be getting warmer and that these algae mats will actually become much more prevalent in the future. Okay, so I kind of walked through then what I would say are some pretty good lines of evidence that many birds are in fact responding to climate change, from rain shifts all the way down to disease outbreaks. And what I hope you can kind of start seeing here, and I sort of following Stan's talk on Tuesday, to me, really, we wouldn't be able to say any of this without the use of citizen science. Citizen science has actually been critical. People collecting information, the general public, for collecting biological information has absolutely been essential for being able to document the ecological impacts of climate change. And where I see this going in the future, and this is actually one of the first Christmas bird counts that were done in 1900, and they've been done every year since then, that these data sets have actually been pretty valuable, and we're only becoming more valuable. I think we're going, and we already are going mobile applications, use of smartphones. We're seeing in crowdsourcing and actually having people help analyze the data. And so really what we are beginning to see is the fusion of disciplines across science. And so I just got off the plane from a meeting in DC, meeting with NASA about 3 hours ago. And for the last 3 days, most of these scientists who are experts in satellite observations and remote sensing, almost, I'd say 70% of the projects were incorporating citizen science in some form or another. And that's a real shift. Now we're having climatologists, remote sensing, ornithologists, data management, computer science people working together with these groups to actually think about how to attack these problems in an interdisciplinary way. And to me, citizen science is really one of the cornerstones at which sort of we're aggregating around. Where I see it going is this. And to me, eBird is one of the best examples of this. So this is an online checklist program. They get over 5 million observations per month that people are submitting using their smartphones, and they're doing this throughout the entire globe. When you've got information like this, we are in a whole new era of being able to look at the distribution of species, the abundance of species, and how the environment changes that. So much so that we can start modeling these distributions. This is tree swallow. You can start seeing their migration pathways. This is a model that's built on eBird observations. We use climate, we use land cover to do this modeling, and you can start seeing this is their breeding area, their fall migration, their overwintering area, and they're coming back into spring, settling into their breeding areas, and then going back down. So we're now actively building this model for hundreds of species and being able to use climate data and other sources to actually build these models. But it wouldn't be possible without people enlisting in eBird and contributing those data. So I kind of put forward then, although we've got the science, we really continue to struggle with the conservation. And to me, I would say some of the obstacles to actually promoting climate-smart bird conservation clearly are external to our scientific community, right? I think we all know that. There's plenty of naysayers out there who talk about climate change and distract from what needs to happen in terms of a broader conversation. But at the same time, there are obstacles even within our own community. And I do a lot of sort of reaching out and talking with managers and conservation planners. And I heard stuff like this all the time. We can only talk about adaptation. So meaning we can't talk about mitigation. That's just too politically charged. Okay, so yeah, we can talk about adapting, but in terms of any like real active role in terms of reducing fossil fuel emissions or even in our own sort of behavior, we can't really talk about that. Climate change diverts resources from more urgent problems, invasive species, environmental pollution, habitat loss. And so climate change is getting way too much sort of scientific attention. And my point about that is that we can't look at these things in silos, that there's clear interactions between all these different factors that are happening. Solutions only exist at broader scales. I'm a manager, I take care of my own property. There's nothing I can do with respect to climate change and managing against or for or buffering species or trying to reduce their overall vulnerability. Communication is not what we do. We are scientists. Okay, we shouldn't have to go out there and try to communicate or talk to or tell a message. Okay, and that's a big problem right now because we need more people to be effective communicators of climate change. So in terms of like what you can do and what I oftentimes talk about, obviously things that I think we all sort of recognize: energy efficiency, energy smart technology. I'd say continue to talk about it. This is a major one. You know, talk about it with friends, talk about it with relatives, talk about it over the dinner table. Because you'd be surprised where most people get their information on climate change. It's not from, I think, in many cases, sort of reputable sources. Be a citizen scientist. Go out there, collect data. We need it. And with that, I'd kind of end on 3 numbers. What's that number represent?
1 planet.
I always get that answer. That we definitely have 1 planet.
1 person.
1 person.
Ourselves.
But what's 1 represent? From what I talked about in the beginning.
Is it the fact that we've warmed 1 degree
Yes.
so far?
Over the last 100 years, we've warmed 1 degree. Everything I talked about today has been in response to that number. Everything we've done in terms of scientific research over the last 20 to 30 years has been in direct response to that number. What's that number represent? The amount of warming that we expect to see in the next 50 years if we stop fossil fuel emissions tomorrow. What's that number represent?
Warming if we stay on the same pace with fossil fuels.
Yes. in the next 50 years, that's the amount of warming we'll see if we basically keep going as we are going. Okay, so I always end in saying we ain't seen nothing yet. When we start thinking about how birds and how other wildlife populations are going to be impacted by modern climate change. And with that, I'd be happy to take any questions.
Thank you. I know that birders are, I consider them the most active of all citizen scientists. They've been doing, they're just absolutely devoted. What's another group that is, I'm just wondering if, for example, if they're hunters or fisher people, what's another big group that's...
Yeah, it's a great, actually, it's a really cool question. I think there are different groups that are becoming comfortable and interested in citizen science. So, for example,
in observing and collecting and sharing.
Yeah, and so a really good example of this, we've got a program out there called Snapshot Wisconsin, okay, where we sort of use camera traps. And people deploy here in the state. There's over 1,000 people that are part of the program. Almost 70% of the people in the program are hunters. Okay, because that's a tool they're used to, camera traps.
Right.
Of those, almost 80% of them have never even heard the word citizen science. Okay, so for them, this was a whole new sort of exploration and sort of integration and exposure to citizen science. So sometimes it is just finding the right tool for the right audience for them to become involved, but they're great. They're really interested. They want to know how the data are used. Almost every sort of study I've seen on why people do citizen science is to better inform scientists, to be able to inform conservation. And so I think that's a strong motivation. I think that cuts across a lot of different groups.
Okay.
Yeah, sorry, yeah.
Is there a way to control the algae growth in the lakes?
Yeah, so I'm probably the wrong person to talk to about that.
Where's it coming from primarily? Runoff?
Phosphorus, nitrogen. It's a lot of runoff from land use surrounding, surrounding the lakes. Agricultural uses, all that fertilizer ends up in the lakes. You combine that with zebra mussels, and I forget what the number is. It's crazy, but there's so many zebra mussels in these lakes that they can basically recycle and filter all the water in the lake in Mendota in like a week or 2 weeks. Like, it's an amazing amount that they do. And so these are invasive mussels that are basically allowing sort of the lake systems to become clear, increasing water clarity, more sunlight, more algae. So I think that combination of things, Steve Carpenter, Chris Kucharik, these are people over in limnology who've been studying this stuff for decades, and so they would have much better sense of kind of what to do. But they definitely talk about sort of informing surrounding land uses. They're worried about more extreme events, more extreme rainfall events that tend to wash more of the runoff into the lake systems. So, yeah. Yeah.
Clean Lakes Alliance is a Madison company that does a lot of that too. I recommend looking at them up for that. And Kucharik does work with them too.
Yep.
My question is about neotropical migrants.
Yeah.
It sounds like you're obviously saying that they're going to have a hard time adapting due to that gap in their chronology. What would be the one conservation, if you could maybe like 1 or 3 conservation goals that would really help neotropical migrants in particular, do you think?
So I think some really cool work has been done on when you have a more heterogeneous land cover, a more heterogeneous landscape, you have less possibilities for a phenotypic mismatch. And that's because these different insect populations are kind of spread out. They're more adapted. In a really homogeneous sort of, let's say, a completely oak woodland, everything is kind of erupting at the same time. And so they have shown that in areas where you have a much more sort of a mixed forest type, that you have less of this sort of real synchronized food resource and sort of the shift, and that mismatch is less problematic. So that's definitely sort of one thing that people have talked about as a potential strategy for reducing that phenotypic mismatch, is to try to have a more diverse sort of habitat types and to have a more diverse resource base, basically prey base.
I have a question about avian botulism.
Yeah.
Is that global phenomenon?
Sorry. So the question is, avian botulism, is it global? It's a good question. I do think they've seen it definitely in other countries, and it's certainly been found in almost all the Great Lakes. Yeah. Yes.
I have a couple questions regarding citizen scientists. Is the program as extensive around the rest of the world that it is in the U.S.? And if it's so successful in the U.S. and you have these grassroots people, why isn't there more acceptance of climate science?
Okay, so the first question is how sort of globally widespread is citizen science? Now, I would say it really is a global exercise. You know, the Britons would say we've been doing this way before you guys, yes. And it's certainly true. They really did pioneer. Schrock and Gibbons did the first atlases. They have really been sort of the pioneers of getting the public involved. And it spread really throughout Europe. So Europe did a fair amount of it. They are doing actually. They really are doing a lot more of it now in Africa too, especially to kind of look for poaching. And so there are a lot of sort of more targeted citizen science efforts in sort of different developing countries. It's definitely a global exercise. In terms of, the other question is, if so many people are doing this, then, why isn't there sort of a broader acceptance of climate change science, and so forth? So I think the answer to that question is that there are a lot of people who do this, but it's a drop in a bucket, right? So Feeder Watch is a good program. We get 20,000 people. That's for the whole U.S. out of 365 million people. So I think there are a lot of people that are engaged in it, but I still think that it's not at the point where they're going to be able to sort of shift the tide, I guess, or shift the conversation. What I would say though is that it really is an important sort of way to sort of reach out. I think as scientists, we need to do a better job of tapping into other groups than we have traditionally, in terms of trying to get them more involved in citizen science. So with Snapshot Wisconsin and the hunters, that to me was one of the first times I've been able to say, yeah, we really are tapping sort of a new group of people that we haven't before. And in doing so, you can have that venue, that opening to education. So look, what I would say about climate change communication, it's really tough. In fact, there's a lot of people who study climate communication on this campus, who say that climate change, that term, you can't use it anymore. Because as soon as you use it, you've already lost the audience. And they've shown time and again, scientists have this tendency to be, okay, in order to change your mind, I'm going to show you more data. Okay, you don't understand, you don't believe this because I haven't shown you enough. So I'll show you more figures, more graphs. What they've shown time and again, and they've shown this pretty cool experiment with people on, I think with biofuels, but if you have people who sort of favor it and people who don't favor it, okay, the more data that they give them, the more information they give them, the farther apart, the more ingrained they are in their sort of beliefs. And so you were actually, before you gave that information, they're closer together. And so what they do talk about is trying to make these more personalized messages. Not say climate change is happening, but try to talk about aspects of their own personal lives that may be affected. It could be anywhere from fisheries, it could be, it could be stormwater runoff. It could be a bunch of different things, but trying to make a more personal message for people to really appreciate the changes. Because that stuff people will agree on, but the term climate change has become so politicized that it's almost lost its meaning, its effectiveness.
Well, what are we supposed to use? We gave up we can't use global warming.
Yep.
Now we can't use climate change. So what's the new?
I think it's just more of these personal stories. I think it's more of trying to figure out what resonates with people in terms of their own personal sort of experiential sort of their own experience on how these things will affect their own lives. And you need the right messengers, and they've shown this time and again. I'm pretty sure it's not Leonardo DiCaprio. And they need to find who can be the messengers for these different groups.
very
Yep.
much.
Thank you.